Hello to everybody and welcome to this video. Today I would like to show you how to model bolt preloading with Abaqus and Hypermesh. To do so, I will use the flange connection geometry, a 3D model, without a 3D CAD of the bolts. So in this case, I will simulate the bolt preloading using wire elements, 1D elements in this case. Bolts are 14 millimeters diameter. So the material for all components will be steel with these properties. Abaqus units I will use are Newton millimeters, tones, seconds, and well, Kelvin. I'm not gonna use temperature, but anyway, Kelvins. Loading definition, we will make two different steps. The first one to make contact, in the second one I will define a loading step which a C load of 30 kilonewtons for each bolt. So the target in this exercise will be to be able to get the preload stress due to this bolt pretension. So having this into mind, we can start the exercise now. So we can go to Hypermesh. So I have opened Hypermesh here and I have loaded the CAD, the necessary CAD. In this case, two components, two flange connection components. In this case, I will need, after having the mesh created, I will need some reposition of the components. So I have here the components. So first thing I'm gonna do, I'm going to just edit a little bit the CAD geometry, just pressing F11. We have this menu. This is quick solid on surface edition. I need to create some washer splits. So I will hide one component. I will create few washers with offset value of 5 is fine. Yeah. So this will be helpful to have a nice meshing near these holes. So you can do it to the other part. Okay, so we can isolate only the flange 1 and we will go to Automesh, to the Automesh. So we will select all the display surfaces. Size, element size will be 5, is fine, with trias. Mesh. And I will modify a little bit mesh style our trias set surface onto these surfaces. To me it looks better with this kind of elements. Okay. Okay, so we can change this stage, we can change the color a little bit to make it better to see. So I will make the flange to current and display this one. So the same process, F12, Automesh, select all the displayed faces, mesh, mesh style, set surfaces. Okay. So now we are ready to create the 3D mesh. So we go quickly to 3D tetra mesh, select the component, split quite in the trials is fine, create per volume components, and mesh. So here we have we can delete this one, yes, and this will be our flange 2. Isolate the flange 1, and do the same, select the component, create per volume, mesh. So now we've got, well, we can delete this one first, 2D mesh, sorry, yeah, and this will be flange 1, can change color again, okay. So at this point we need to reposition both components, so we'll quickly go to tool, position, elements, green one, by attached, and we will select from this to this and this node position. So now the interfaces are coincident, so it looks fine. So what I need to do now is just go to component, create component, and call it rigid. We can color it red, but first of all we need to go to 3D element types and select tetra 10. Yeah, this is fine. So we need to change order. Select the displayed and change displayed all and change to second order. It's fine. We need to change this option again back to inside of rectangle. And now we can create the rigids. So we go to 1D rigids, multiple nodes, yeah, it's fine, and calculate node. So we first of all, I'm going to do once. I will pause the video and do it myself. So I'm going to explain it this one. So we need to go to select the nodes, select one by face, and now we need to press Shift, right click, outside of circle. Okay, so again, press Shift and hold right click of the mouse and select this circle. So now we have all the nodes selected to create this what our rigid. Yep. So I will do the same process for each hole. So as I said, well, I have created one rigid for each hole, for each component. So what this rigid does is just give the same displacement for all these nodes, the same displacement as this node has. So if this node moves in X direction, all these nodes will move same displacement, will have the same displacement in the X direction. So between these rigids will be beam elements representing the bolts. So what we need to do first is just quickly press F4 and select nodes between the rigids. Okay, these rigids, this node and this node. select nodes between here too, and clicking nodes between. So the same, do the same for each rigid. I will pause it. Okay, so I've done it for all now. So now we need to go to here, right click, create beam section. Okay, so we will go, okay, select this and radius, say 7 millimeter section. Now quickly we will create the property section, property, okay, bolts. I will say this is beam section, yes. I need to create the material first. Go right click on material, renaming as steel. Here I will select elastic with this as Young modulus and 0.3 as Poisson ratio. So now we have the steel. We go again to bolt property and select material, steel, and beam section they created before. So yeah, this is a circle with 7 millimeters. Yeah. So now we're here. We're going to create the property for flanges. So this case will be solid section, yes, with material steel. And now we are going to select both flanges, pressing Ctrl and selecting the property 1. Okay, so now they have assigned the property. Yep. So quickly go to component, right click, create bolts. Okay, so at this stage I would like to show just rigid and bolts, so isolate only. We have the rigids with the nodes created before, so we just go to 1D, bars, bar 2. So we need to create 3 elements, bar elements, between both flange connection. So node A, this one, node B, this one, and here we need to make sure we are going to select the direction node, the same one, for example this one, in each case, for this one, and this one. So I'll show you. Okay, one thing, Ctrl Z, here we need to select bolts property. So again, select node A, this one, node B, this one, and direction node, this one. Okay. Yeah, to see if the property has been properly assigned, we can go to here and select 1D traditional. So yeah, looks fine. The section is applied to the beam, to the bar element. To complete the exercise, we can go back to this view, and again, node A, this one, node B, this one, and direction node, this one we set. Okay, this is important. Again, this one, node B, this one, and direction node, this one. Okay, I will do the same for all of these. So I will pause the video. I will show you right now the whole bolts. Okay, whole set of node bolts. So here I am again. I have completed all. So it's very important. The element types of the bolts are B31. Okay, so again we can go to this view and represent the bolts. So they look fine. So we're back to this view. One thing we need to create is 5 nodes in top of these rigits to apply the loading. So quickly go to Tool, Translate, and select the top nodes. Oh, sorry. Be careful selecting these nodes. And now we click in Duplicate, and we will translate it following the plane defined by these three nodes. So translate. It doesn't matter the magnitude, just 20 is fine, 10 is fine, whatever. So return. Now we can show flanges. So we have all in order. So having said that, we need to now create the contact face between both flanges. So we quickly go to Tool, Contact Manager. So we need to create the surfaces. We are going to hide flange 2. So flange 1. 3D solid gasket elements, all of these. We may, hide these elements and say display. Proceed, faces will propagate by face. Proceed, add. And now we do the same for the flange 2. So just quickly go to surface, create new, flange 2, create, attached, it's fine, faces, propagate by face, proceed, add. So surfaces are created, we need a surface interaction, create new, interaction. So we can add friction, friction type default, 0.1 is fine, 0.1, okay. So quickly go to interface and create contact pair, contact. So it doesn't matter in this case which surface is slave or master. I will do this way. It doesn't matter. The interaction will be the interaction just created. Parameter adjust 0.05. So I will select surface to surface, and everything else will remain as default. Okay. So now we are here in interface. We need to create one pretension section for each bolt. So we need 5 in all. So I will show you how to do one. I will create myself the others. So preloading, preload 1, I will call pretension section, create. So at this point I will show the bolts, rigid, I will hide this one. So we have this, for example, this one will be the first one. So we have, I will hide the groups, hide. Okay, we have 3 beam elements, and we have one node in which we will apply the loading pretension. So here we need to define pretension definition element, select the one in the middle, okay, and pretension node definition, select the created on top, proceed, and okay. And that's all. I will do the same for the rest of the bolts. Okay, so I have finished the preloading definition, pretension section definition. As we can see here, don't worry about this, but we have this node selected as pretension node. In reality, we have selected this one, but this looks like an error from Hypermesh. So don't worry about this. So just continue. Another thing, the preloading, I will define the loading in these nodes at the end, just changing the INP input file so will be at the end. So now what I'm going to do is just close this dialog, okay, and create the sets to apply the boundary condition. So we will clamp this end. So just select these nodes. Okay, and now I'm going to create another set called preloading nodes. I'm going to select these nodes. Oh, sorry. Shift, right click, and select this one. And now select these nodes. Proceed. So I think this model is ready to be imported to INP. So export. I will call job 3 preload INP. Export all. Yeah, I can export all. So export. And we will open it now. So if you open the input file with Notepad++, you will see all this piece of text code. So we need to go to the end and I will paste the steps. Just right click, paste. So I just pasted the steps necessary to run this model. So the first step starts here and finishes here. So this is the make contact step. I will say boundary condition here. I will need to define the boundaries. So I will say boundary condition 1 to 6 degrees of freedom are constrained. And this one means that the preloading nodes set created in Hypermesh let's see, the preloading direction will be X. So the direction 1 will has a displacement of 0.01. This is like adding a pressure to make contact. So don't worry about this number. It's just to make sure the contact is done. And we will write these output field variables to see all different kind of variables as strain, stresses, that's fine. So the second step is the preloading step. So what we need to do is just write the preloading nodes. It's important the name is the same as the set created in Hypermesh. So in X direction, we will apply 30 kilonewtons. Yep, and what we need to do now is just copy these two lines and paste them here. It's very important, this one. We need to say star boundary OP equal new. This will delete these two. But we need to remain, we want this one to remain, so we just write it again, but not writing preloading nodes, okay? So this will change everything. So yeah, the preload step, we have the boundary condition boundary and the preloading nodes. Okay, so we can save it And we can go to Abaqus now and run the model. So we quickly go to job. This is very important to have the set working directory. In my case is fine. We go to job. We go to job manager, create from input file. Okay, so we select the preload created before, continue. So we leave everything as default. Okay, and we can submit. This analysis will take like 10 minutes run. So I will pause the video. I will show you the results, how to get the results after. So the Abaqus has run the model is completed. So if we click here in results, we can check the results. So we can click here, here, and show only feature edges. Click here, we can visualize the stresses. In this case, about misses. Can go to S11 stress in X direction. And it says the stress in X direction, I mean in the bolt direction, is 198 megapascals. So a good way to check these results is go to the analytical formula. I have that here. So using this formula, applying the loading and the radius to get the area, we have 195 megapascals. So it's very close, just 3 megapascals difference. That difference, it's maybe due to other parameters. So to me it looks fine, the results looks fine. We can change the options to see the beam elements. So as the red is on the bolts. So yeah, and that's all. This is a good result. We didn't use CAD elements, so soft CAD geometry, just 1D elements. This is a good way to save computational time. Above all is if our models are using many nodes. So I don't have nothing else to say apart from subscribe to this channel. If you like the video, clicking like. That's all. Thank you very much for watching this video, and see you later.